Q tilde coupling to pi and then you have a listy 1 mode which comes in with a Maxwell type term. I just write it as F mu nu, where F mu nu is the normal thing, F mu nu is the mu A nu minus d nu A nu. So that's the spin 1 kinetic term. And then you have minus, from this term here, you get minus 1 over lambda to the 5 halves psi h mu nu d mu pi d mu pi minus e to mu nu pi squared. And that's still somewhat ugly because we have kinetic mixings and it's still not in its most transparent form. But what we do is we diagonalize the mixing terms. So the mixing terms are, this is a mixing between Q and H, Q and pi. So we want to get rid of those mixings. And the trick to do that is to then perform another redefinition, field redefinition. H mu nu is H tilde mu nu plus Q mu nu tilde plus e to mu nu times pi, and that diagonalizes the theory and gives you, when all is said and done, a massless term with the wrong sign kinetic term in 3 dimensions, so that doesn't matter. And then you get a Fiat-Pauli mass term, a Fiat-Pauli Lagrangian with its associated, well, the mass term goes to 0 because we take it m to 0. We get the spin 1 contribution, F mu nu squared, and then we get, from performing this part of the field redefinition that diagonalizes the various mixings, we pick up a kinetic term for pi, and then lastly, this last term gives you the following interaction. And the end of the story, is that all the interactions, as promised, are sitting inside the Licity 0 mode. So the Licity 2 and Licity 1 are completely free in this limit. The decoupling limit focuses in entirely on the interactions of the Licity 0 mode, which are the ones at the lowest scale. And they come in with this cubic interaction, and this is what's called the cubic Galilean. And although not immediately apparent, both of these terms in the Lagrangian, both of these actions are invariant under the Galilean symmetry. Pi goes to pi plus a constant plus v mu x mu. The Lagrangians themselves are not invariant because d pi squared will clearly pick up a, so if we just do it for this piece, d pi squared will pick up a minus d mu pi times v mu. But this is a total derivative. And similarly, this piece, although the Lagrangian is not invariant, it transforms into a total derivative, so the action is invariant. So, as promised, this Lagrangian is precisely that of a Galilean, which exhibits this Galilean symmetry. So, as promised, this particular theory of massive gravity, new massive gravity.
Sorry.
Yes.
Does it have the quadratic calculator?
No. In this case, it doesn't. No.
No.
Yeah.
Why?
It's just a fluke. Yeah. Yeah. Why do you think it might do?
No, I thought because you only impose the Galilean symmetry. So in 3D, I thought there could be like one more when you
go
to higher order.
That's right, but there is a modification of this theory which you can add extra operators, and those will give you the quartic Galilean.
Oh, but not
yeah,
just
not this particular one.
okay.
So this is just a particular special choice.
Okay.
So this was the first theory of this type that was written down for new mass of gravity, and then there's extensions to that which give you all the Galilean operators in 3 dimensions.
I see.
Yeah.
Does that involve the Riemann tensor?
No, it's this. The full general thing is well, I forget what it's called now. It's like a Born-Infeld new mass of gravity or something like that. So you can complete this combination. Turns out you can complete it into basically a square root, like a Born-Infeld type thing. Square root of the determinant of G mu plus G mu, something like that. And then, so that's the full thing, and that would give you the quartic Galilean handcuffing limit. So it's the more general version, yeah. So I just gave you one example which illustrates the point I wanted to make. Okay. So, okay. So that shows you that you have this Galilean, but I haven't really told you why this resolves the BdVz discontinuity. And the key point is actually what's gone on in this process. I had to do a field redefinition where I shifted h mu nu by pi. Now, so we started out with h mu nu coupled to t mu nu, and if we shift h mu nu by pi, then what we'll generate an extra coupling where pi couples to t. So that's the Licity zero mode coupling to the trace of the stress energy. If we just do the free field answer and we ignore the interactions, then that will give this extra fifth force contribution, which is responsible for the BdVz discontinuity, and gives you in 4 dimensions that extra plus a 6 contribution, the difference from the minus a half to the half. And in 3 dimensions, it's difference between -1 and minus a half. So it's this guy that is precisely responsible for the extra fifth force that, if that were the end of the story, would rule out this class of theories. But we see that this guy has this extremely non-trivial interaction. And so let us ask, at what scale does this interaction become important? And I'll do this for the d-dimensional case in general. So, let me go back to d dimensions. And I will consider for simplicity the cubic Galilean in d dimensions. So that's just the same thing. Minus r pi squared. And then in d dimensions, this scale is 1 over lambda 2 plus d minus 2 over 2, and pi squared log pi. And then in general, this will couple to pi t, and then that would have actually been the square root of M3 here. So it's not square root, it's just no, it's square root. 3. In general dimensions, that would be Planck to the 2, to the d minus 2 over 2. So this would be the kind of thing you would get in a massive gravity theory in d dimensions, and I'm just for simplicity going to truncate to the cubic Galilean to see what we got. So let me put my hand over that and then just solve the linear theory. And let's just take a point source, which would correspond to stress energy being just a mass term so we're in d dimensions, so that means d minus 1 space dimensions, and so I'll just take a point source in d dimensions. Then if we solve the linearized theory, we're solving some equation of this form. Box pi goes like t over np to the d minus 2 over 2. And that's just the standard, if we look at static sources, that's just the standard Poisson equation in d dimensions. And so we know the general solution for that goes like pi, or scale like m, the mass of the source, times m Planck to the d minus 2 over 2 over distance r to the d minus 3. So if we're in 4 dimensions, that's the standard 1 over r potential. If we're in 5 dimensions, it's the 1 over r squared. If in 6 dimensions, 1 over r cubed. So this is just the analog of the Newtonian potential in the appropriate dimension. So it's because this is the same equation that you would solve for the Newtonian potential. So that's what you would get if you just solve the linear theory. So we can ask at what scale does this nonlinear term become important? And so let's think as coming into the source. So we have some source at r equals 0, and that's come in. As we come into the source, this potential gets bigger and bigger and bigger because r is getting smaller. And so we expect this quantity to get bigger and bigger, which indeed it does. And there will be some radius at which the nonlinear term is equally as big as the linear term. And so that is the radius when we transition. So we have a point source here. There will be some radius where outside here the field is described by the weak field. And inside it, it will be described by, it will be a strong field in the sense that we'll have to solve the full nonlinear equation. And that radius is set by the scale at which d d pi over lambda 2 plus d minus 2 over 2 is of order 1. Because that is the thing, that combination, that Galilean invariant combination, sets the ratio of the cubic term to the linear term. And so plugging in what that is for a mass of a source, that's the scale at which m over m Planck to the d minus 2 over 2 times r. So I'm differentiating twice. I'm going to lose 2 powers, so I'll have d minus 1 there, times lambda, the 2 plus d minus 2 over 2 is of order 1. And if I rearrange that and plug in what lambda is, this is the scale at which r is comparable to 1 over d minus 1 times m over m squared m Planck to the d minus 2. Because I've just written lambda back in terms of the mass scale n and the Planck scale. And this scale is called the Weinstein radius. Because it was Weinstein that first realized that generically in the theory of mass of gravity you will have this scale arise, and it's the scale which sets the scale at which the transition between when I can trust the linearized theory, when I have to solve it non-linearly. He of course didn't do it through this decoupling limit calculation. He was thinking of it just at the level of the full theory, and he was looking at a theory that had a ghost at that time, but his argument was nevertheless sufficiently generic that it gave the correct answer there. So we see that Weinstein radius is proportional to a positive power of the mass of the source in 4 dimensions. It goes like the cube root of the mass. So the bigger the source, the bigger this radius is. Now what happens effectively is outside of this radius, the VdVz discontinuity is active in the sense that you'll get the wrong prediction for gravitational bending of light if you fix Newton's constant by the static contribution. But inside this region, you can't trust that linear calculation, and effectively what happens is that you recover the prediction of you basically recover the prediction that you'd expect from just GR. And I'll convince you of that in a second. Because what happens is that this scalar, velocity zero mode, becomes strongly coupled and then can't effectively propagate the force between matter in an efficient way anymore. And so the effective force it propagates becomes actually negligible. Now let me put you some numbers in that just to get a feel for what that is. So if we look at our solar system, we take m to be the mass of the sun, and we take, for example, the graviton mass to be ordered the Hubble scale, which is typically what you imagine in these scenarios, massive gravity scenarios that say something about cosmology. You don't want to change gravity until you hit the cosmological scale, so you take that to be the Hubble scale today. Then the Weinstein radius for the sun turns out to be something of order 150 parsecs, which is a big distance. It's far bigger than the solar system. And so what that means is that within the solar system, nowhere in the solar system can you trust the weak field approximation. So the VDV discontinuity, which naively would rule out the theory of massive gravity, is in fact not relevant in the solar system because this extra degree of freedom is strongly coupled all the way out to this distance scale. But in fact, it's even better than that, because once you go out to 150 parsecs, there's a lot of other matter out there. You're going out to galactic scales, and you have to include the mass from all that matter. And so when you include the mass from that, because this goes as a positive power mass, you get an even bigger Weinstein radius, and which means you get a bigger Weinstein radius, you have to include all the mass from that. And you keep going and going, and what you find is that effectively the Weinstein radius always turns out to be the Hubble scale today, because that's the natural scale in the problem, because we've set the graviton mass to be the Hubble scale today. And so once you keep going and you include all the mass in the universe, you end up just having the Weinstein radius being the Hubble scale today, which means if this effect, if this Weinstein mechanism works as I promised it should work, then you will, in a theory of massive gravity, you will have no difference between Einstein gravity all the way out to cosmological scales, and it's only at cosmological scales that things become different. And that's one of the things that makes these theories extremely attractive, because it doesn't mess up all the standard predictions of Einstein gravity that we've tested at solar system scales for pulsars and so on. All of those come out just the way you want them to, and it's only at cosmological scales do these theories prove to be actually different, and then that's why they're kind of interesting for exploring alternatives to dark energy and alternative explanations for what the cosmological constant is, and trying to potentially say something useful about that. Okay, so let me try to. So far I've only told you that things become nonlinear here, but I haven't actually proven to you that the force is small. So let's just do a simple calculation. So I'll focus in on the four-dimensional case, and I continue to work with the cubic Galilean and take the stress energy T to be just a point source. Then in that case, for the cubic Galilean, the equation of motion for the Galilean looks like prime here is an R derivative. I'm just looking at the static source. So we're going something like this. The Planck R squared. And if I integrate that up, I get the pi prime over R plus 1 over lambda cubed. Pi prime over R squared is equal to m over m Planck 4 pi R cubed. And so the two regimes are, in the weak field regime, this is the equation. So the weak field, which is R much bigger than R Einstein, then pi prime, which sets the force, looks like a contribution that goes like 1 over R squared. And so that gives a fifth force, which is comparable to the ordinary Newtonian gravitational force, which is why you have the VDVZ discontinuity. But if you then look, if you look in the region where R is much less than R Einstein, then in that region you can just take this part of the equation, and you're taking the square root, and then pi prime in that region will go like, you're taking the square root. So I'll jiggle it around a little bit. So it goes like m over 4 pi in Planck. It will go like 1 over square root of r times r of Einstein to the 3 over 2. But the key point to note is that pi prime goes like 1 over square root of r rather than 1 over r squared. And we're looking in the region at small r. So if I look at the ratio of those two forces, if I look at the ratio of this force to the ordinary Newtonian potential, so we'll look at the force coming from pi divided by the normal Newtonian force, then in this region, this is an order 1 factor, which is why you have the v div z, but within the Weinstein radius, you get something that goes like m over 4 pi m Planck 1 over r Weinstein 3 over 2 r to the half divided by the ordinary Newtonian force law, which scales something like this. It's like 1 over r squared. Now rearrange that. And now I'll ignore the order unity factors. This will scale like, let me get the right way around. I'll get confused. This will scale like r over r Einstein to the power of 3 over 2, because it's 1 over r squared r to the half, so you get a factor of 3 over 2. So within the Weinstein radius, the force, which it comes from the derivative of pi, from the fifth force due to the Newtonian force will scale like r over r Einstein to the 3 halves. And remember that inside the Weinstein radius, r is much less than r Einstein, so this force is much less than unity. And this effectively describes is the Weinstein mechanism. Due to the nonlinearities, pi no longer successfully propagates a fifth force, and it gets suppressed by this mechanism. And if we plug in these numbers, so if we take m to be the mass of the sun again, just because it's the most massive thing in the solar system, and we take the graviton mass to be the order of the Hubble scale today, as is typical in these scenarios, and we look at what the extra fifth force from the sun is on the Earth, so we take r to be the radius of the Earth, then this factor, for these scales, we're so well inside the Weinstein radius that r over r Weinstein is of order 10 to the minus 12. So that is a remarkably successful screening effect, which is what we call the Weinstein mechanism, by which this force becomes negligible inside the Weinstein region. Are there any questions on that? So it's this that resolves the VDV discontinuity. As we make the mass smaller, we make the Weinstein radius for a given source bigger and bigger and bigger. So we make the region in which we can trust the massless theory, Einstein-Hilbert gravity, to be bigger and bigger and bigger. And it's only at extremely large distances do the modifications coming from the mass actually kick in. Okay, so I'm running out of time, so let me give you one last piece about this Weinstein mechanism. What I've done is essentially compared the contribution of the force from, let's say, the sun, from this pi field to the Newtonian force from the sun. You've seen that suppressed. But there's a little more you can do about that, so let me more generally think, let's think of, back to the full theory. we can see the Einstein mechanism in a bit more detail as follows. So I just focusing on 4 dimensions. So let's think about the solar system. So the sun is the biggest mass in the solar system, but there are other masses in the solar system. There's the Earth and the Moon. So suppose we want to consider the force between the Earth and the Moon within the solar system, taking into account the Einstein screening from the sun. We want to understand whether the force between the Earth and the Moon is also suppressed once we've accounted for the Einstein screening from the sun. And the way we can do that is, what we're basically saying is we think of the stress energy as the stress energy of the dominant mass in the system, which is the sun, plus some small perturbation, which is the rest of the solar system, i.e. the Earth and the Moon, for example. So we think of splitting this up into a background contribution plus a perturbation. And then associated with the background contribution from the sun, we can split pi up into a background contribution from the sun plus perturbations. And look at what happens for the perturbations. Now this interaction is a non-trivial kinetic term. And so when we expand around a background, having a non-zero verb for the background will effectively renormalize the kinetic term for the fluctuations. So let me just do that and split it in. So if I substitute that decomposition into the action and expand to quadratic order, then what happens is that the action for the fluctuations around the background will have this form. It will have some renormalized kinetic term, which is a function of the background field times d mu delta pi, plus, and then delta pi will couple delta t. And so the Einstein works in a little more detail. Not only does it sort of screen the overall effect from the force from the leading object in the system, it also screens the force between everybody else by the following mechanism, by renormalizing the kinetic term here. And what this renormalized kinetic term, what I've done is written an effective metric, which is basically e to mu nu plus d mu pi bar over lambda cubed. So as we go into the Einstein region, this thing becomes large, and so the effective metric becomes large, and at least one of its eigenvalues will become much bigger than unity. And to see that that effectively makes the coupling between two sources small, what we can do is just canonically normalize this system. Now, this is not proportional. It's not. This is actually a tensor, so there's no trivial canonical normalization, but this is scalar. But let's just be crude and imagine that z mu nu approximately takes the form e to mu nu times an overall scale, which is not true, but just for simplicity, let's imagine that. So then this looks like a wave function renormalization. So then what we can do in this system is canonically normalize this field. The canonically normalized field will be delta pi canonical over square root of z, with this wave function normalization. And after we've canonically normalized, this z will go away, and then that will put this z down here in terms of the canonically normalized.